Well, thanks for having me. And I'm talking about dark matter at the Future Collider. Right. So the motivation for studying dark matter is it's a little bit different from the top-down point of view. And it's not a requirement in the consistency of the theory that we have to have dark matter, but it's an observational fact that we do have them. And it's the only, I would say, observational evidence that we have particles, new particles beyond the standard model. So now, but we can try to think about what kind of candidate, what kind of dark matter candidates are there, just based on the fact that we observe the role they play in forming the structures in the universe. And but that gives you a very big range. So this. So they give you almost roughly 80 order magnitude, their mass can be. So this is a very big space of possibilities. And, the next step, what you wanted to do is to look for a convincing story that will be your first part, first place you start to look for dark matter. So one set of compelling story is the following: that maybe we see massive particle already, we see particles with interactions. Maybe dark matter particles are not so different from them. They will have weak scale mass and the weak scale couplings and so on. But the radical abundance of dark matter is determined by some very early universe physics. So it would be ideal if their abundance somehow does not depend on, in very great detail, of our knowledge of the early universe. So, and one obvious idea is that if they are a consequence of a thermal equilibrium in the early universe. So you all know that this is the familiar story of WIMP. So, and so this is the well-known WIMP miracle. I may not go through it, but it relies on the dark matter coupling with the standard normal particles not being too weak, and the dark matter particles being, with mass around the GeV scale, and we get a correct radical abundance out of this story, and this has been a major hint for us for weak scale new physics. And if you put in the numbers in a little bit more detail, and you will see that this is this is the number. So if you put in, for example, the standard model gauge coupling, which is on the order of 0.3, the G square is on the order of 0.3, you will get a dark matter mass around 1.8 PeV. So let me remind you, if you asked me 10 years ago, I think, how many years? Maybe 7 years ago, this is where everybody thinks that dark matter will be discovered. So dark matter is part of a much bigger complete model. And so here I'm using SUSY as an example. So at LHC, you will start to produce those colored super partners, such as Bluino and the Squark. And they follow a very long, complicated decay, and give you a lot of observable particles in the detector, and dark matter, being neutral and stable, is at the end of the decay chain, and you don't see them in detectors; they form missing energy. So these are very good signal for a machine like LHC to look for, and the standard story is that the dark matter will be produced this way and have this spectacular signal, and we're going to discover dark matter together with the answer to every single question we have, such as naturalness and so on and so forth. So, and one thing you notice that the dark matter here is not directly produced from the collision itself. Therefore, whether the reach of dark matter is necessarily correlated with the reach of these kind of color particles. Of course, this has not happened yet, as we all know, and this is probably one of those limit plot that you see, and this is for this particular one is the correlation between is gluino and the dark matter particle mass. You see that the reach of dark matter is correlated and is limited by the reach of how much. For example, you're not possible to discover a dark matter particle that's heavier than the gluino. Okay. Of course, this doesn't mean that this picture is out. Okay, so it's still very plausible, as you have heard from previous talk, and of course, this will still be the focus of a lot of new physics search when LHC turn on the next year. And if we go into higher energy machines later on, and we'll have a automatically higher reach for this color particle, we'll also have a higher reach for the dark matter particle mass. On the other hand, so in recent years, there has been a lot of, I would say, rethinking about exactly if we just focus on the dark matter particle problem, and what is the basic channel, what is the most model independent channel to see dark matter. So this is one of those very basic channels. So you have to pair produce dark matter from standard model particle coupling. So this is the same picture I drew earlier on with the WIMP miracle. This is the interaction that you really rely on in this WIMP story. But of course, if you just have this, you see nothing. You have to recoil against something. So either a photon or a jet, for example, or something else. This goes by the monophoton, monojet, or mono-X story. And this has also become a pretty standard LHC search at this moment. There are a lot of limits. Let's see. Now, if we still consider a SUSY-like, but simpler SUSY models, just with the SUSY dark matter. Okay, let's see what those kind of simple channel can do. And so I'm using the SUSY as my example here, not just because we love SUSY, but also SUSY LSP actually forms a very simple. In SUSY, there's several possibilities for what LSP might be, and they actually form a set of very good examples just of even simple dark matter models. So for example, Bino is also known as a singlet dark matter. Xeno is a pair of doublet, and the Wino is just an electroweak triplet. Okay, so in other words, even if I don't want to start with SUSY, I just want to consider a set of simple dark matter models, and I will probably start with this list as well. Okay, so this is a very good starting point to think about just the general strategies of general dark matter search. Now let's consider a little bit of detail. So because we do have that WIMP story, we have some constraints on the dark matter in detail. The dark matter relic abundance cannot overclose the universe. This actually in SUSY, focus us onto these several possibilities. There's this pure Xeno limit, and a pure Reno limit, and the so-called will temper, and the co-annihilation limit. In both cases, there is something that's fairly close in mass to the dark matter. So all of these, at least these four possibilities, all characterized by, there's some very small mass splitting between the dark matter particle and the next particle up. Okay, very, very small mass splitting. In these cases are chargino and the neutronino. In this case, it's just some other super partner. So what is the generic signal of things like this? Okay, again, I remind you, this is the standard story. I have this long decay chain. I've seen a lot of those energetic particles. But now let's focus on the case I only have a very small mass splitting. Then, in that case, the decay product, so this is still my dark matter particle, this is the particle, the next up particle, and then the decay product between them are very, very low energy, and it's so low that you cannot, usually you don't see them in the LHC detectors. And therefore you still have to, in order to observe this kind of event, you still have to rely on this whole thing recoil against some energetic particle. Okay. And so therefore, we again back to this our basic channel, which is this is the only observable object in the event. So this is monojet, monophoton again. So our previous discussion of monojet and monophoton applies very well in this case, in this very general class of models. And LHC, well, first of all, at 8 TeV, there's no limit in because it's, the background is so overwhelming. And LHC 14 only have a very, very small, very limited reach in the monojet channel. And this is even under some favorable assumptions about systematic errors. And this is for LHC 14 running, many, many years, accumulated 3 inverse Erdogan of data. Okay. So this is in the deep future still, that you see the reach is very limited, only a few hundred at most. So by the way, so this is the 2 sigma exclusion limit, and this is the 5 sigma discovery potential. And so from this on, I think you see that the LHC 14 is probably not the ideal machine if you want to explore a lot of the parameter space in this wave story. Okay. So you can ask 2 kind of questions. First is that what a higher energy collider can do. So I'm going to just show you some results using 100 TeV PP collider as example, but you can get an idea if it's slightly more energy, if it's even more energetic or less. And you can also ask, can LHC 14, can we do more? Okay, so I will focus on this first, and if I have time, I will briefly mention some of these things too. So let me first talk about the possibility of going to higher energy. And so going to higher energy is just a very simple fact that automatically you increase your mass reach a lot. So this is again in the Wino case, but so this is what 100 TeV can do for monojet, and this is what this is the same curve I showed you earlier. What 14 TeV can do. You see, there's a pretty big increase in terms of reach in mass, and there's a big band here because this is a very challenging channel, and it's usually dominated by systematics. So therefore, anything. If we're thinking about design the future collider, a lot of focus needs to be focused on what a detector needs to do to reduce all possible systematic errors. And this is a similar plot for the Higgsino. I'm just going through those few cases I mentioned earlier. This is the well-tempered where you have a very small mass floating between the NRSP and the Bino. And the novelty here that is you may be able to even see some of those decay products as very soft leptons. You don't trigger on those things because it's too soft, but you can still trigger on this very energetic jet and look for the soft leptons later. And it turns out to be very useful in this case. Okay, it can basically beat your background a lot. And this is the so-called co-annihilation. This is I think the stop. If a stop is very close to Bino in this plot, and this plot is if a Scurino is very close to the Bino, and both of them has very impressive reach gain going from 14 to 100. Just because this is the optimistic case, I'll say, because this is the production cross section is big because you're producing a colored particle to begin with. That's the reason that these set of plots are much bigger. Had much bigger reach than the previous ones. So this is just a brief summary of what monojet result at 100 TeV reach is. You see that it's an impressive enhancement, a factor of 5.27 compared with, this is a typo here, compared with LHC 14 TeV. Okay, compared to LHC 8 TeV is the infinite improvement because at LHC 8, the limit is 0. Okay, so, and this is compared with LHC 14. But on the other hand, this is still very, very challenging because the systematical errors is completely dominant in this kind of search channel. And the question is, can we do more? And I think the answer is definitely yes in the we know case, and I remain hopeful that we can still make more progress in other cases. But let me just briefly show you what the we know case is. So in we know case, and there is a very small mass splitting between the chargino and the dark matter particle. When the mass splitting is very, very small, the decay is from that chargino, the charged particle produced to the dark matter is very long-lived. So the charged particle will actually get into the detector and going through the tracking system and then decays. When it decays, it gives you a very soft ion and the dark matter particle is escaped. So this kind of signature is very strong, and it's called a disappearing track. Okay? Just to get a feeling about what this kind of channel can do, there is a current Atlas search just based on this channel, and the current limit they can set on we know is about 250 GeV. Okay? 80 EV data. Okay, this is very impressive because again, like I said, based on monojet, there's no reach, there's no limit on the we know yet. Yet this channel is so strong that it can already reach to 250. Okay. So therefore, it's not surprising that at any future colliders, I expect that this really is going to be the dominant. This disappearing track is really going to be the dominant channel in the search of a we know particle. So this is what if you just simply extrapolate that Atlas search to a 100 TeV machine, and this is what they can do. So again, this is where LHC 14 can do, and the LHC, not the LHC, the 100 TeV PP collider can do much, much better. So we also have a set of constraints coming from, for example, indirect detections from we know annihilated by a loop to a pair of photons because they are dark matter particles. They were annihilated in the galactic halo. We can try to observe those photons from Fermi or from HASS or CTA experiment. So these two experiments actually, HASS can already set some pretty strong limit on the we know parameter space, and CTA will be even stronger. But one thing to emphasize is that these kind of limit is very much depend on the kind of the so-called halo profile. Halo profile you are using, if you're using some, the halo profile basically means how the dark matter particles is distributed in the galaxy. And then this annihilation rate goes by the number density squared. So it's very, very sensitive to the kind of dark matter particle distribution in the galactic halo. Okay, so this is just putting things together. I think we know, particularly because of this disappearing track type of technique, can be completed. All the parameter space, allow the parameter space for we know can be completely covered by a 100 TeV PP collider. So that's just it's much stronger than the monojet case. And more broadly, let me just, so this is sort of a summary slide for the 100 TeV case. So what I said is that the LHC is good for dark matter, roughly in the range of 100 GeV, couple hundred GeV, and 100 TeV PP collider will start probing into a TeV range of dark matter mass. As I showed earlier, this is really where most of the parameter region of the wind dark matter should be. And at the lepton collider, of course, it's a very clean machine. It gives you a very solid limit, but it's limited by the center of mass energy. Okay. So now let me just come back to the second case. Is there anything else we can do beyond the just monojet and some mediocre reach, limited reach of dark matter particles? Yes, in the case of, I think the answer is yes, but it's in the case of somewhat more extended models. And these are the so-called simplified, but it's not so simple. Okay, this model simplified mediator models. So there are two possible ways. If I just think about it, the dark matter can couple to the, for example, standard model quarks. It can either go by this or this. So this is called S channel. I think it's, drawing this picture, assuming time going up, and this is called the T channel. And so this can be, for example, either a scalar or a C prime, for example, in this way. And this can be just some kind of a squark-like particle. And I call this as not so simple because in contrast to SUSY, whereas in SUSY the mediator are the known particles, and WZ and Higgs. Okay, these models are not so simple because you have to add in another new mediator to the story. So immediately you already see that adding a mediator makes actually quite a bit of difference. So first of all, you can still look at the monojet channel, and so you see this big resonance structure in the monojet limit. But moreover, I think it's usually the case that if you add a mediator, you should actually try to directly search for the mediator. Let me just go back quickly. So because this guy couples to QQ bar, so you can imagine that you can also reproduce this guy back from QQ bar initial state and it decay back to QQ bar. Okay, so this is also known as the digest resonance. Okay, so and it turns out this digest resonance search, even the CDF digest resonance search, is already stronger than what LHC can ever do for the monojet in this case. Okay, so this is the overarching story here is that once you add a mediator, it's usually easier to just discover the mediator itself. So another way of sorry, this is just what a future collider can do with this kind of stories. So for example, 100 TeV collider can do obviously very well in terms of looking for heavy digest resonances kind of mediators. So this, yeah, so notice again this unit here is TeV, so you get a TeV region. And there's a similar story in the so-called T-channel mediator story, let me not go through this too much because I'm running out of time. But in general, you can still study the interplay between a monojet search and an actual mediator search. This kind of mediator will be more similar to a squark-like search. Okay, so this is a paper I did with Haipeng and Hao Zhang. And so where we actually discuss the interplay in the ATV case, but the message I think is general, and the process involving the mediator direct production always gives you the stronger limits. In other words, it's always easier to discover the mediator itself than the monojet. Okay, so let me just come to my conclusions. So I think search for dark matter is already, and it will continue for a long time to be as one of the central themes of new physics research in the future. And SUSY-like models give you a very good representative set of possible dark matter already. It's very challenging, only have a very limited reach at LHC. For that, we really need to think and work harder, maybe use tracks. But the most important thing is to expand the reach in this kind of models is to go to a higher energy machine, to really probe a majority of the wind parameter space. And on the other hand, at LHC, what we could do, and it's being done, is to study some of those even more extended models by adding new mediations. Okay, thank you.
You mainly talk about the monojet and final states, right? But you also already showed us that in ATAS there is the PK mode, including the missing track, in the better connectivity than monojets.
Yeah.
So, I mean, I agree with you that SUSY-like model can provide a way for us to search for the dark matter because it's anyway in SUSY. In the R-parity conservative SUSY models, there always a margin between ET in the signation. So this will, of course, is also a signation for dark matter. My question is, for the SUSY-like models, which do you believe the most sensitive channel? It's not necessary to be the model as you already showed. So you give the sensitivity for the several GeV or several TeV, then this is based on model search.
Yeah, perhaps I should say, in a more, in SUSY-like models. So it depends on what you mean by SUSY-like. If you start to actually energy is enough to produce those colored superparticles, and the gluino and the squark, of course, your reach is going to be driven by the production cross-section of those guys, because those guys decay to dark matter. But what I'm considering here is an even simpler set of models. Let's take a SUSY-like model, but only look at the neutralino-chargino sector. Okay. The reason is that this set of dark matter model, actually, you can think of them as go way beyond SUSY. They encompass a large class of possible dark matter models. They are either doublet or like Higgsino or triplet like a Wino. Okay. But for Higgsino, for example, for Wino, there's this special thing you can do with the tracks. For Higgsino, it's much harder. I think for Higgsino, the most sensitive thing I'm aware of is still the Mama jet. Okay. So.
This one, yeah, real quick comment and also one person. You talked spend much time on the so-called thermal winds, which we call wind miracle. There's one more the production which is non-thermal, which is like the most, and the Gaudi also thing proposed called a non-thermal wind miracle. So the question is, how your studies on sensitivity rely on assumptions on the production of winds. And if you change all of that into the non-thermal wind, this will change your result?
Well, so for the SUSY-like model, in particular for the models that the Gaudi likes, and this is golden because disappearing track is the way to go. He likes Wino or speed. So sorry, I should say that the reach just depends on the quantum numbers, right? It depends on whether it's Wino or Higgsino. If it's a triplet or it's a doublet, it's fixed by standard model gauge coupling. Okay, so now whether it actually gives you the full radical abundance of the thermal radical abundance really depends on its mass. Okay, if we know it's lighter than 3 TeV, you have to rely on some of the non-thermal production mechanism. Okay, but the reach here doesn't depend on it. The reach is. Yeah. Yeah, WIMP is just a motivation, right? So it's a motivation to think about this class, general class of particles.
Can I just add a quick comment about that? I mean, it's just a general fact, not specific here, but it's a crucial thing about looking for. I mean, it's really crucial to just find any stable particles. It's really crucial to find any stable particles at the colliders, and that's the best thing about just directly producing them is that you learn that there are stable particles there, and of course, if you literally make like if you make exactly a 1 TeV Higgsino, exactly what it takes for it to be irrelevant, that would be pretty good evidence that it is irrelevant. But in fact, anything which doesn't look like that is teaching you something very interesting about cosmological history, or about the presence of additional dark matter. Maybe it's half axions or something. So I think on all these plots that there could be overlaid something. Sorry, there is on many of the house something about if it's a thermal history, what fraction of the dark matter the particle is making up. I think we should be interested if it makes up 10, 20% of the dark matter even, right? We could have multi-component dark matter. It could be very interesting from many points of view.
We know how this scales, right?
Yeah, of course we know how this. We know how everything scales. But I'm just saying that
weakly interacting particles in the few TeV, in the 1, 2, 3 TeV range, are in the neighborhood where they give you interesting levels of relic abundance, and also in lots of top-down theories with non-thermal production, they give you interesting levels of that, right? But that's it. Then if we see it directly at accelerators, if there's too light or too heavy, we can get direct evidence that it's not thermal, that we have additional component of dark matter, non-standard cosmological history, so it would be even more interesting.
I want to ask a question. In the F-channel or T-channel mediator dark matter model, what is the mass of the mediator or dark matter come from?
What is
The mass come from what?
Oh, so it depends on what this mediator is. If the Z prime, it has to have its own Higgs and
The T-channel mediator.
Oh, T-channel. T-channel. Well, it's again depends on what this is. If it's square, it depends on SUSY breaking. But if it's some other general T prime, then it depends on your model. It could just be a vector like, or it could be just I don't know. I mean, it really depends on model.
It's not if it's not S particle. It's a new model. So.
Right. So for example, these guys, dark matter can be scalar, and this will be a fermion. Then it really depends on how you give the fermion mass. If fermion is vector-like, you can just write the mass. If it's chiral, you have to have some new Higgs again. So
some new physics.
Yeah, new Higgs again. If it's chiral.
Okay, let's learn a mental game.